Both will get into much more complicated. So everybody else has clearly So this way you can how's everybody doing? Okay. Okay, so last time I realized, based on the questions that people were asking, that something I wrote down could be written in a better way to make it less controversial, let's say. So that's where we'll start, more or less where we left off last time, but we'll back up just a little bit. So if you remember, we're talking about connections to statistical lower bounds. Okay, and here's a setup. If you remember, basically we have some parameter, theta, which has distribution pi, okay? And pi lives in some set of admissible priors. So maybe, distributions with second moments at most 12 or something, okay? And then what we observe is x condition on theta going according to some conditional distribution. Okay? And here what we notice, okay, is that we have the Markov chain theta to x, so theta hat of x for any estimator theta hat. Okay, so what was not controversial is that I can write by beta processing inequality. Okay, there's less than or equal to beta x. Okay, and then just trivially, this is less than or equal to supremum over distributions on theta, let's say in my set of admissible pairs, mutual information between theta and x. Okay, so this part wasn't controversial, right? Now, the part that was controversial was when I wrote something down on the left-hand side and people were asking, well, how could I get a certain constraint in the bottom? So let's write it this way. Suppose my estimator theta hat is such that expected loss between theta and my estimate, theta hat with x, is less than or equal to L. Okay, so just found a long piece of chalk, properly broken into 3 pieces. Okay, so suppose my estimator is such that the expected loss is at most L. Okay, no problem. then I claim that I can write this as greater than or equal to the infimum over conditional distribution such that expected loss between theta and theta hat is at most L, mutual information between theta and theta hat. Okay, do you agree with this? Yeah? Because if theta hat is such that this is satisfied, well then certainly if I optimize over a larger set, here the conditional distribution don't have to go through X. This is just any theta hat jointly distributed with theta such that the expected loss between these two things is almost L, right? So this mutual information here is of course no larger than this one here, right? Because I could always take my particular estimator or it lies in this set, right? Okay, so very good. So what can we conclude? Let's call this guy the rate distortion function evaluated at L, right? And let's just, for sake of notation, call this guy the capacity of the channel from theta to X, okay, with admissible inputs living in this set P. Okay, so just for sake of definition, let's define these two quantities. And so then what I can do is I can summarize that RL is less than or equal to CPX theta. Right? Yeah? Very good. So now here's the thing. If we define A's risk as we did last time, this is defined as the infimum over estimator's theta hat, the expected loss between theta and theta hat X, right? Then what I can conclude is from above, because what this tells me is that there exists a sequence of estimators, theta hat, right? Where I can make this L as close to the Bayes risk as I like. Do you agree? By definition, right? Because the fact that this is the infimum over estimators equals this, it means I can find a sequence of estimators that have loss L getting as close to R phi theta as I like, right? As close to the Bayes risk. Definition. Okay? So that means over here I can take L as close as I like to the Bayes risk. Okay? Now, the rate distortion function is a convex function. It's continuous. Okay? Except maybe at the endpoint where it blows up to infinity or something like that. So, anyway, the conclusion is because I can take L as close as I like to the Bayes risk, and this is a continuous function, okay? I conclude that this inequality holds. Okay? You guys agree? So this is what I wrote last time on the left-hand side as I was running out of time, and it seemed to be pretty controversial because people were like, well, how can you put R star down here because it seems like that's the best, so maybe there's only one thing in here, or whatever. You see the argument now? Does this clarify? Yeah? So it's like basically we have a bound for any loss, okay, for which that can be achieved by an estimator, and then, basically we optimize over the estimators, and we get a bound like this. Okay, so this left-hand side here is a monotone decreasing function in its argument, right? Okay? And so what this is, since this is a monotone decreasing function, and it's upper bounded by something, this altogether is giving me a lower bound on the Bayes risk, right? Because as I try to make that Bayes risk smaller and smaller, imagine if it was a free parameter that I could adjust. Okay, since this is a decreasing function, I'm making the thing bigger and bigger as I make its argument smaller and smaller. Okay? But it's upper bounded by something else. Right? So eventually it'll crash into that, right? So this whole thing, okay, the moral is that this provides a lower bound on the Bayes risk. Right? And that's what we're after. We're after statistical lower bounds, namely lower bounds on the performance of any estimate. Okay? So far this is like an entirely generic procedure. Okay? So generic as to be essentially useless, I guess, because we haven't really used any structure of a program besides simple things like data processing and definitions, essentially. But generally speaking, considering here on the left, if we look at it, it depends only on the prior pi and the loss function L, right? We've eliminated the observation model from this left-hand side, okay? And likewise over here, this depends only on observation model P at given theta and possibly my set of immiscible priors P, right? So it's actually, by going through this procedure, you're essentially decoupling this problem of trying to prove a statistical lower bound, okay, into computing one quantity that depends on just some subset of the parameters, and computing another quantity that depends on another subset of parameters. And oftentimes this is easier than trying to evaluate the Bayes risk directly, okay, where you'd have to optimize over all functions of the observation, okay? So again, like I said, this is a generic procedure, okay? Basically what I've written down is a lower bound on Bayes risk, okay, that holds under extremely general conditions, okay? Basically no assumptions were made. So let's see how this will be implemented in practice, okay? Because at this point, like I said, basically so abstract to be basically just topology, right? Okay, but the idea is we know how to compute rate distortion function and channel capacity for a lot of canonical problems. Things like additive Gaussian noise, Hamming loss, squared loss, whatever. So let's take an example, concrete example. Okay, Gaussian local model. Okay, so here's the basic idea. We consider x equal theta plus z, okay, where z is normal, let's say, d-dimensional Gaussian random variable, or random vector, okay, independent of theta. Okay, and then let's just, for kicks, okay, take my set of immiscible priors to be the set of distributions on RE such that the second moments are across, let's say, sigma squared times d. Okay, so the trace of the covariance matrix is sigma squared times dimension. Okay, so roughly speaking, it looks like the average variance per component is sigma squared. Okay, just constrained in some way. Okay, so this is our setup. Good. And so let's just try and evaluate this generic bound that we came up with for this concrete problem. Okay, so for upper bound, evaluation, okay, we just have mutual information between theta and x. Okay, I just wrote out the definition of x is equal to mutual information between theta and theta plus z. Okay. And so if we supramize this over theta in our admissible set of priors, okay, we did this computation before in one dimension, but it's no different here. This will be precisely d over 2 log 1 plus sigma squared. Okay, take d equals 1, for example. We saw the capacity of the Gaussian channel is log 1 plus SNR. Okay, that's precisely the formula that we're recovering here. It's the same thing. Just use the fact that Gaussian maximizes entropy subject to second moment constraint, and you're good. Okay, so the evaluation of the upper bound. Okay, so let's consider the lower bound. Okay, evaluation of lower bound. Also did this computation before for L2 loss. Okay. Evaluation of lower bound. Okay. And let's choose for the particular prior. Say, for choice prior, where I assume that theta is Gaussian, okay, with variance sigma squared in each component. Okay, standard Gaussian scale by sigma. Right. No way to say. Okay. So evaluation of this lower bound. The minimum mutual information, okay, between theta hat and theta, subject to the squared distance as m most phase risk. Okay, now we did this computation before also. This computation was computing the Gaussian rate distortion function. Okay, so in fact when we evaluate this, we get this is equal to d over 2 log sigma squared b over pi star over the base risk. Okay? And so what I see is when I compare this upper and lower bound, okay, remember we have this bound here, I evaluated the left-hand side here and I evaluated the right-hand side here. Okay? So when I combine these things, okay, then what do I find? I find that the base risk is at most sigma squared b over 1 plus sigma squared, and the base risk is for the prior pi equal 1 sigma squared b. Because this particular choice of prior was in the set of distributions, right? Fine? Okay, very good. So for this particular choice of prior, what we find is that base risk is at least this. Very good. Okay, and so note if we observe xn conditional IID copies of x, right? Then basically what happens is the computation is almost identical again, except for what we get is that the bottom becomes n sigma squared. And you can do the computation directly over here, okay, to see that if instead of x I had xn here, okay, n conditionally IID copies of x, then the idea is that it's basically like boosting my signal to noise ratio by a factor of n, right? But you can just evaluate the mutual information directly using the same formulas, basically. Okay. Very good. So, let's see. So typically, what people are interested in, or oftentimes what people are interested in, are these so-called minimax lower bounds. Okay? And what is minimax lower bound? Minimax lower bound. Okay, so the minimax risk is defined as, let's say, which we denote by R star, is defined as minimum maximum risk. Okay, mini-max. Yes, question?
Yeah, I had a question. So here we're trying to find a bound for the base risk we're given prior. But you say that prior comes from like some pure mesh family, but why would the bound depend on what family it comes from? Like we can just redefine our family, right? And then tell you if the bound would change.
So, okay, one of the points of going through this procedure, so what we obtained is base risks for a specific prior. For any other prior, okay, good luck computing this mutual information here, okay? You might be able to bound it or something like that, but in general, good luck. So oftentimes what people are interested in are these so-called minimax risk lower bounds, okay? And what the idea here is, so I'm going to answer your question shortly, essentially, but the idea here is we look at the minimum, let's say, minimum risk over all estimators, okay, where we maximize over the distribution on the parameter, where we maximize over the prior, okay, in some, let's say, some other set. I'll call it P tilde. This P tilde doesn't have to be the same as the other, okay? And this is expected loss between theta and theta hat x. So minimax risk is called such because the idea is that you choose the estimator, okay? And then an adversary gets to choose the prior, the distribution over parameters. It's like they get to choose worst case. You see what I'm saying? Because I play first, I choose my estimator, and then they go, right? And so the idea is just by trivial max-min inequality, this is greater than or equal to a sup p theta in p tilde in theta hat. Okay, expected loss between theta and theta hat x. Okay, now this here is precisely the Bayes risk for prior p theta, right? By definition. So the whole thing, right, is greater than or equal to the Bayes risk for any prior in this set p tilde, right? So in proving a minimax lower bound, it suffices to be able to compute the Bayes risk, or lower bound of Bayes risk, for just one choice of prior. You see what I'm saying? So in general, it may be very difficult to find a lower bound on Bayes risk in general. We'll talk about a general technique in about 3 lectures or something like that, okay? But for now, what you see is that we used our choice of this specific prior here, so that way we could evaluate this mutual information, okay? Or this lower bound, essentially, right? Now, of course, you're right. We evaluated Bayes risk for a very specific choice of prior. But in order to get a lower bound on the minimax risk, all I need to do is be able to lower the bound of Bayes risk for one choice of prior. And so this is often how these arguments proceed. Someone wants to bound minimax risk, okay? So what they try to do is bound Bayes risk for a nice, convenient choice of prior. Gaussian in this case. You see what I'm saying? So here, if we continue this, sure would be nice if these boards didn't cut one another off like that. Okay. So if we continue this example, what we have is we have that the minimax risk, okay, in this particular example, let's take P tilde equals set of densities, or this probability distributions on RD, okay? So this is truly minimax in the worst case sense that I choose an estimator, and then the adversary gets to choose any prior they like. Okay? Anything they like. And in this case, we have that this minimax, or this minimax risk, okay, is greater than or equal to phase risk for my particular choice of prior pi, right? But in fact, I can choose my prior as I like. And in this case, I can supermise over the parameter sigma squared. Okay, because this was phase risk, okay, where this was my particular choice of prior. And so any choice of prior gives me a lower bound on the minimax risk. So this is so what you find out is this, right? Because I'm after a lower bound on minimax risk, I was able to establish a bound on base risk for this particular class of priors, right? And so now I obtain a lower bound on the minimax risk just by optimizing base risk over this class of priors that I was actually able to execute the computations for. Does that answer your question?
No, my question was that like when we found this lower bound, it depended on the upper bound, which depended on P, which is distributions that which pi lives in. So it seems like we can optimize over P to get a better upper bound against a better lower bound.
Yeah, in principle, right? Well, also in principle, I could just compute the base risk directly, right? If I could compute all these things. So the trick is to try and choose classes of distributions for which you can actually execute the computation. So here, the idea was, if I chose P to have finite second moments, then I could evaluate this upper bound, right? And I could evaluate this lower bound, and the upper bound doesn't depend on the prior at all, right? And I could evaluate this lower bound, which doesn't depend on this script P at all. I was able to evaluate this lower bound by selecting the choice of prior, pi, of this form. You see what I'm saying? So by taking clever choices of both pi and script P, I was able to evaluate both the upper and lower bound. And what this does is it gives me a bound on phase risk, okay, subject to some constraints, the constraints that I imposed, right? Namely, this is the phase risk under this assumption, right? Okay, phase risk under this assumption, when, okay, the prior satisfies the second moment constraint, right? And so now the idea is, this is good enough though to get a minimax lower bound. Because minimax lower bound, again, just doing basic, using definition, is lower bounded by base risk for any choice of prior, essentially. Okay? And we got a nice lower bound on base risk, okay, for a nice class of priors. One parameter here to optimize over. And so now I just execute the computation and I see a minimax risk is lower bounded by D. Right? That's a nice, concise conclusion. And so let's take an example, or let's note, or observe. If I take the sample mean, okay, this is equal to theta plus 1 over n sum zi I equal 1 to n, okay, where zi, IIP, standard normals in d dimensions, right? And so what you note is for sample mean, okay, for the sample mean, what we have is that the expected loss okay, is equal to 1 over n, okay, expected 1 over square root n, sum of 1 over n, zi squared, okay, but when my choice of normalization here, this is standard normal. So this is precisely d over n. So here's the point. Minimax risk is equal to d over n in this case. Conclusion. For a Gaussian local model, okay, the minimax risk for this I equal to theta plus standard normal. The minimax risk is precisely d over n. Okay? Because the idea is we got a lower bound of minimax risk, okay, through the generic procedure that I outlined. Right? And so that lower, well, we first got bound on base risk for a particular class of priors. We use that to get a lower bound on minimax risk. Okay? Fine, because any bound on base risk bounds minimax risk. Okay? And then here, much easier part, we showed that it's achievable. For a particular choice of estimator, namely the sample mean, this achieves risk precisely d over n. Okay, regardless of theta. Right? So the idea is for this Gaussian local model, minimax risk is precisely d over n. And the optimal estimator is just sample mean. Clear? It's actually not trivial, right? Because I can evaluate this part immediately. I could say, oh, for sample mean, okay, the risk is d over n, okay? But to show that this is best possible, show there's nothing else that I could do, some really clever transformation or whatever, okay, it's not entirely trivial, right? Okay. In this case, I guess you could use sufficient statistics. This is just basically shows how one would implement this procedure. Okay? The idea is that these information quantities are kind of like universal currency. Okay? It doesn't matter what loss function you're dealing with or what the distributions are. If you can execute this procedure here, okay, which again is a non-trivial thing, unless if you're working with specific choices of priors or whatever, then maybe evaluating these things is not so easy. But if you can evaluate them, okay, then this basically allows you a way to compute base risk, which is basically the approach to establish min-max risk lower bounds. Okay, min-max risk lower bound, you basically choose one specific prior, and this gives you a bound. Everything clear? Yes? No? Okay, so let me just write down more. Good lower bound get this motion function for some class of priors. Okay, plus good upper bound on capacity of channel px given theta for some set of input distributions. In this case, our set of input distributions were those with finite second moment. Okay. Equals, okay, max lower bound. Okay, so this is where the art is, okay, being able to evaluate these two things. Otherwise, after that, it's just plug and play. Okay, this was the only work that we actually did. Okay. Any questions? Yes.
Could you Lyon's particular example, the lower bound matches the true value?
I mean, the short, snarky answer is that all the inequalities are equalities. Yeah, I mean, the Gaussian case is like very, very special, okay? Because not only do we get a lower bound on minimax risk, you know, in both dimension and number of samples n that matches the upper bound, it like matches in constant factors also. So often what's the case is that you're dealing with a more complicated example than this Gaussian model. And you maybe, if you're lucky, get a lower bound of minimax risk and an upper bound that match up to constant factors. So maybe there'll be like, you know, maybe you'll have something like this, if you're lucky, okay? Or something like this, if you're less lucky, okay? And so if you look through the statistics literature, okay, you'll see all sorts of basically results on minimax risk where they just give an upper bound and lower bound. It's extremely rare for them to match up to constants, even like in this case where we have d over n precisely. And so in this particular example, I think the answer why all of the inequalities end up being equalities is because the Gaussian example is just very, very convenient for many of these computations. And somehow it works out to both be like, the best input in order to achieve the capacity of this channel, in some sense, because if I put in, for Gaussian channel, Gaussian maximizes input. And then it's also, in fact, you see this in your homework, it's also the thing that maximizes the rate distortion function subject to second moment. So Gaussian source is, in some sense, the hardest source to compress subject to second moment. So Gaussian has this kind of extremal property, in a sense, that, it basically minimizes the capacity, okay, while simultaneously maximizing the rate distortion function. And this, roughly speaking, I guess, is attributed to something called Gaussian saddle point property, which we don't have the tools to prove yet, but we'll eventually acquire them and I'll assign it in your homework. But I think that somehow extremal property of the Gaussian distribution is what all of this boils down to and gives equalities everywhere. It's not a very concise answer to your question, but the short answer is we just got lucky, okay? Because Gaussian is very nice.
Could you provide an example of a different kind of product that we could both evaluate and find the lower bound to be worse than the Gaussian case?
Yeah, so here's an example. You did it on your exam, okay? So basically what you can do is basically lower bound or find a bound on the rate distortion function using like maximum entropy type things or whatever. Oftentimes those evaluations won't be tight, but maybe they'll give you the right answer up to the constants and varying correctly in the parameters that you care about, namely dimension and number of samples. The other thing that you saw was on your homework, you have this problem on so-called Shannon lower bound. It's closely related to that exam problem actually, where it basically gives a generic method for lower bounding rate distortion function under some constraints. Okay, and then oftentimes, okay, in terms of the capacity, again, if we have like certain types of maximum entropy distributions. So Gaussian is one maximum entropy distribution. We observe additive Gaussian noise subject to second moment. Okay, so we can basically evaluate the capacity of bounded in that case. So there will be other examples. There's sort of like exponential noise channel and things like that. I would say that this is a common thread of capacities or mutual informations that we can bound quite explicitly. Is usually they involve some sort of maximum entropy distribution. So again, that's maybe not a really explicit concrete example, but I could come up with one. It would just take me a while to work it out. Yeah, but looking in those family of things I just mentioned is enough to basically give you some examples. Yeah.
How to give the upper bound for minimax values?
The upper bound for minimax risk comes from basically constructing an estimator. In this case, we propose sample mean as our estimator, and we look at its performance.
That's a lower bound.
No, this is upper bound at minimax risk. because I chose the estimator. So that infimum is upper bounded by this particular choice of estimator, right? Yeah, usually the difficulty is improving the lower bound. Okay? Maybe, at least from my perspective. Oftentimes if you have an optimal estimator, oftentimes it's fairly easy to describe. Something like a plug-in estimator or whatever. Yeah, actually, this would be a good homework problem. So maybe I'll assign a homework problem for your question. Okay, so that way you can evaluate it. I mean, it's basically the same steps, really. You just maybe will get upper and lower bounds that don't match up to constants. Now, another answer to your question, or someone else's question, is how do we evaluate this capacity in general? Right? Okay, if we're not working with, say, this Gaussian model or whatever. So, as I mentioned earlier, I don't know if I answered it in direct response to the question, but we will see a general technique for bonding mutual information in a bit. Okay? We don't have the language to state it yet, but we will soon. Okay? Just be patient. Okay, so we'll establish a whole bunch of Bayesian type of bonds. Frankly, I think that Bayesian bounds are more interesting than minimax bounds. Okay, the reason why people appeal to minimax bounds or resort to establishing minimax bounds is because it's generally very difficult to establish a Bayesian bound for a particular prior. Okay, so as you see, the minimax bound is easier in this case because we just contented ourselves with establishing a Bayesian bound for a particular easy class of priors. Okay. So let me point out something. So in this example, we used the fact that under our assumptions, the mutual information between theta and n conditionally independent observations, okay, behaved as logarithmic in n. Okay? Right? This is, I mean, we didn't write this down explicitly, but this was in the evaluation of the channel capacity, basically. And then we put the n sigma squared in there for the signal to noise ratio. So, in general, okay, hard to do, much better than linear n. Because if we just appeal directly to chain rule, okay, in properties of entropy, this is something like h of xn minus h of xn greater than theta. These things are conditionally IID, and this thing is bounded by the sum of the marginal entropies, so this is less than sum, or n times, let's say. So right? Okay, so if we just use properties of entropy rather than the explicit formulas for the Gaussian channel that we were able to take advantage of, we would have gotten a very suboptimal bound. Okay, we would have been off by basically an exponential factor. Okay, so in general, we'll see how to fix this later. Namely, that for under basically very general observations, we'll be able to show that this behaves logarithmically in n, roughly speaking. Okay, but again, that will take some patience. So now what I want to talk about is an alternative, okay, method for basically establishing lower bounds. Okay, and this introduces a new type of information, namely Fisher information. Okay, many of you have probably heard of Fisher information. How many people here have heard of Fisher information? How many people understand what Fisher information actually is? Okay, that's what I expected, actually. Because Fisher information is like this. How many people have heard of mutual information? Okay, those whose hands aren't up. So, how many people after getting to this point in the class have some warm fuzzy feeling of what mutual information actually is? Still no hands. Okay, more hands. The idea is mutual information information, at least for me, maybe it's just because of my training, but at least for me, okay, it really satisfies this warm fuzzy feeling of what information is, right? It's, made it a very precise way through these coding theorems that, literally X is revealing a certain number of bits about Y, okay? So Fisher information, I have no idea why they called it information. Actually, does anyone know when Fisher information, presumably Fisher proposed his information, and whether he called it Fisher information? He probably didn't call it Fisher information, he probably called it information. Anyone know what year it was? I have no idea, but I'm curious whether it was before or after 1940. Maybe he was just, maybe he was earlier, maybe after. I don't know. Okay, anyway, so this is what we're about to introduce. Okay? So it'll take us a few minutes to get there. Okay, and a little bit of new terminology. But it'll set us up for later. Okay? So Kramer bond. Okay, Kramer bond is basically a motivation for introducing Fisher information. Okay, let's say Kramer bond and Fisher information. Okay, so I'd like to introduce Fisher information in a slightly more general context than maybe you've seen it before. Okay, maybe that sounds like bad news because already you've seen it before and you don't understand what Fisher information is. And here I'm going to try to give you a more general viewpoint on Fisher information. Not really more general, but likely more general than what you find on Wikipedia, I suppose. Okay. So here, what we need to do is we need to understand the concept of measure space. This sounds scary, but it's not, okay? And the idea is you'll just be able to keep in mind concrete examples throughout, okay? So let x lambda be a measure space, okay? Here the idea is x is just our alphabet, okay, in which our observations will take values. Lambda is a measure on this alphabet. What is a measure? Just think of it as being a probability measure, or some scaled version of a probability measure. Okay? Think of it that way for now. Okay? Very good. And let the standard notation is to use semicolon, so I will use semicolon here. Okay? F dot theta, so these are functions. Okay? Theta in some set theta, subset of RD. Okay? B in indexed family of probability densities with respect to the measure lambda. It sounds complicated, okay? It's not. What does this mean? It means that f x theta is greater than or equal to 0 for all x and x, theta and theta, okay? And the integral of x theta d lambda x, okay, I'll explain this in just a second, over x, over space x, is equal to 1. Okay. That's what it means for these things to be an indexed collection of, for this is for all theta, in big data. Okay? So let's take some examples to make this more concrete, because the notation is new. Okay, and this concept of measure space may also be new. But like I said, just think about it as a probability measure. Okay? Very good. So some examples. Okay. X is Rn. Okay, pretty concrete. And lambda is equal to so-called Lebesgue measure on Rn, which means E, that notation d lambda x is the usual dx. Okay? So in this case, the f's are just a bunch of regular probability densities as you know them. Non-negative functions that integrate to 1. Okay? The reason for the somewhat may seem convoluted at this point, but the introduction of the additional complexity here in the definition is that we're not always observing things in Rn. Okay? Maybe our observation is some discrete space, X. Okay? So let's take another example. So this is example 1. Okay? X is discrete, and lambda is equal to a so-called counting measure. Okay? On X. And what does this mean? This means on E, let's say for some G, X, d lambda X, this notation then means that we're just taking some X in X gx. Okay? So the idea of d lambda x is basically the infinitesimal weight that the measure assigns to an element of x. Okay? So the Lebesgue measure is basically a measure that assigns two sets, the volume of the set. Okay? So when I compute the integral of a function with respect to the Lebesgue measure, it's just basically I take the function at that point and I multiply it by the infinitesimal value of the line, right? That was the basic idea. In the case of discrete space x, right, the idea is the measure assigns each element of this space, say, equal measure, equal weight, okay? And so when I integrate over this space, it's just adding up the values of the space. And in this case, okay, if x is discrete and lambda is a counting measure on x, then these fx thetas are nothing but PMFs, okay, for each theta. So for each theta, okay, f is a PMF on x. Okay, and in this other example, for each theta, there is a density on a usual familiar sense. Okay? But we can also take d lambda x to be something else. For example, okay, x equals Rn, okay, and lambda equal Gaussian measure, okay, Gaussian probability measure, okay, in which case, in that expression up there, we just replace d lambda x by the Gaussian density, 1 over 2 pi n x minus x squared over 2 dx. So basically, it's just think of now the f's as being not probability densities, but weighted versions of probability densities. Okay? So that way when I integrate them against the Gaussian probability density, they integrate to 1. See what I'm saying? This is it. Okay, so you can actually forget about all of this general business if you like, and in your notes, everywhere I write d lambda x, just write dx. Okay? Your notes will be slightly less general in the sense that you'll just be working for parameters in Rn. Okay, but you'll get the general idea. You won't miss much. Okay. You can Wikipedia about definitions of measures and things like that. The thing is, in general, we don't have to take x to be, say, Rn or x to be a discrete set. my space X could be much more general. For example, X could be the collection of Lipschitz functions on the torus, okay? You see what I'm saying? Like it could be some wacky space. And lambda would just basically be, think about it again as a probability measure. Something that, assigns volumes, if you like, or measure to sets of those functions. Okay, just like the usual dx, when I integrate over some set, it gives me the volume of the set. Same thing. Great. So that seems really complicated, but again, just in your notes, write it out in the less general form if you like. Okay. So we're going to make some assumption henceforth. Okay, this is the usual thing, and I won't make it super precise, but this is a rough idea. Okay? And our assumption is that as a map of x and theta, f x theta is sufficiently nice so that we can exchange orders of 1 integration with respect to x and 2 differentiation with respect to theta is a perimeter in Rn or Rd. Okay, so we're just going to assume that the mapping from x and theta to the likelihoods or the conditional densities fx theta, okay, is sufficiently nice so that way we can exchange these two things. For most of you, you probably would just exchange these things without thinking. Okay, in general, you can have wacky behave functions and you need some assumptions in order to exchange order of integration and differentiation. In general, this is called, is it LBI? Is rule. Look up Leibniz rule, okay? Basically gives you a rule to exchange order of integration and differentiation. And you'll see there's like 3 conditions that need to be met, generally. Okay? So we just assume those are met. And so for example, if we integrate gradient of lambda x, okay, gradient is with respect to theta. Okay? How do you compute the derivative? Right? You know the formula from calculus. Derivatives, at least in the sense that we understand them in this class, okay, are only with respect to a real valued parameter. Okay? Because you do, rise over run, and you take this, the slope or the run as small as you like, right? Definition of limit. Okay, so whenever I write gradient, I'm differentiating with respect to theta, because differentiation with respect to x may not make sense. Because, for example, if x is a discrete space, how do I differentiate a PMF with respect to its parameter? Doesn't make sense, right? You can't differentiate a discrete function. Okay, not in this sense. Okay, so here we go. If we assume that we can exchange order of integration and differentiation, then what this tells me is that I can exchange these two. Okay, but I have the nice property that these things are densities with respect to lambda. So by definition, this integral is 1. Okay? So just 0, for example. This is what this exchange allows us to do. And in most cases, okay, we will be justified in doing this exchange. Okay, as long as you don't cook up too wacky of densities. Okay, very good. So this is the assumption. We'll allow ourselves to freely interchange the order of differentiation and integration with respect to different variables. Okay? As I said, most of you probably would have done this without thinking, except for the few people from the math department in here who would then, agonize and spend weeks over trying to justify why you might be able to interchange those. So, guys know the name, Amir Dembo. Okay, he's a probabilist at Stanford. So his background is actually information theory. He was trained in electrical engineering and now is basically a probabilist. So when he teaches classes, he often times has a blend of students from, for example, electrical engineering, okay, and math or statistics or whatever in his classes. And so he was teaching some class about, I don't know if it was an information theory course or what it was, but one of my friends was in the class, and they told me that what happened was he gave the exam, and all of the engineers left early, and all of the mathematicians were there for the whole time, okay, because they worried about the little details, and the engineers just solved the problems. Funny story. Okay, good, so here we go. So now that we've set up the universe in which we're going to live, okay, let's introduce a definition. Okay, the score, I have no idea why it's called score. It's a completely non-descriptive term, okay, of a random variable, okay, is defined as follows. V theta x, okay? I won't use this notation very much, but it'll be convenient to retain the notation for today. Is defined as the gradient of the log of the density fx theta. Okay, very good. And so log here is always natural log. In terms of Fisher information, we'll always use the convention natural log. Actually, henceforth in this course, let's use natural log, unless I say otherwise. Okay, very good. So what that's going to allow me to do is write this as gradient fx theta. Oh, let me be clear. X is capital X here. Over x theta. Okay, this is a random variable where x is distributed according to the conditional density f beta. Okay, so x is a random variable. It lives on the space script x. Okay, and its density is given by this. Okay, so the score function is just a new random variable, a function of x. Okay, which is obtained by differentiating the log of the conditional density. That's it. Okay, just a definition, nothing more to see here. That's it. Okay, very good. The definition turns out to be justified later. Okay, but this is it. Okay, so observe. Score has 0 mean. Okay, indeed. Let's take the expectation with respect to x here of the score. And note that this is just the integral of this with respect to the density, right? Okay. So this is the score here, v theta x. And I'm integrating it with respect to the density, just like we always compute expectations. Okay, and I integrate over x. And what you notice is that if I write it in this way now, then the densities cancel, and I have by up there that this is precisely 0. Right? Because gradient of log is equal to gradient over the function itself. The density cancels with itself, and I'm left with that expression on the left, which we saw was equal to 0 under our assumptions. So score is a 0 mean random variable. Okay, a random vector or a random something. Variable. Yeah, it's a real valued, or a random vector. Excuse me. Okay. Definition. How much time do I have? Ugh. Okay, definition. Okay, the second moment, or let's say definition, I guess, Fisher information. Okay, is defined to be second moment of the scope. Okay, so we denote it like this. Squiggly I. Okay, there's actually, it's going to get really confusing because there's 3 different types of Fisher information. Okay, so let's pay attention. Squiggly I for this type of Fisher information. Okay, of theta. Sometimes I put a subscript down here, theta. Sometimes I don't if it's obvious, but just to indicate that we're talking about the Fisher information with respect to this parameter theta. Okay, now it's a function of theta. So I don't know, it seems redundant, but in some cases it's convenient to have the thing downstairs. Okay, so I'll just write it there. It's defined as a second moment of the score function. Okay, so this is v theta squared. Very good. And if we just expand it out, we write it like this. Gradient f theta squared over f theta lambda x. Very good. So this is the expression for Fisher information. Seems quite complicated. Okay. Let's take a simple example here. I think the reason why Fisher information is complicated or confusing compared to mutual information, at least for me, is there's really no theorems that tell you Fisher information has this precise interpretation like there are for mutual information. Okay? Fisher information normally comes up in terms of bounding. So here, let's take an example. Okay? If x is Rd, okay, so for all of those people who are writing d lambda x just as dx, okay, to keep in mind that real example, I would be happy with this. Lambda equals the vague measure. Okay, so d lambda x is just dx, okay? And f x theta is equal to g of x minus theta from x theta. Okay, so we're assuming this for some density g in the usual sense, okay? Because now integrate this with respect to dx. That's the integral of this thing with respect to dx. The vague measure, or the usual integral as you know it, okay, is invariant to translation. Okay, so g must integrate to 1. Therefore, it's density in the familiar sense. Okay, so if I have a situation like this, theta is so-called location parameter. Okay? Because what I'm actually observing is x equal theta plus w, where w is density g, independent of theta. Right? That's what this is telling me, this setup. Conditional density of x given theta is equal to basically the shift of the density g by theta. So what it's doing is it's just telling me, okay, observing x given theta is the same as observing x or theta in some additive noise, where the additive noise has density g, right? And so let's compute the Fisher information in this case. In this case, the Fisher information, okay, let's just look at that formula there, is equal to gradient gx minus theta squared over gx minus theta dx. Okay, over Rd. Okay, but now just by change of variable, is equal to gradient G U squared over GU VU. Change of variables. Very nice. Okay? And what you notice is this is no longer a function of theta at all. It's just a function of G. Okay? And so this we define as J of G. I like script J here. J. Okay? J of G. I'll try to write script J, but this is difficult. It looks fancy, so sometimes I'll just be lazy and write regular G. Okay? And I call this, okay, this is what's confusing, is there's these different types of Fisher information that exist, okay? And everyone just calls them Fisher information. So I call this the information theorist Fisher information. Okay? And I call this guy statisticians. The only way to tell the difference is if you're consistent on notation. Okay? So the thing is, statistician's Fisher information is a function of a parameter. Okay? See what I'm saying? For each, basically there's some model of observations, namely some collection of conditional densities conditioned on a parameter. Okay? And so for each choice of the parameter, the statistician's Fisher information gives me a different number. Okay? And the rough idea is how much information, again in some very warm fuzzy sense, is the observation revealing on average about that particular parameter. Okay, theta. I fix the theta, this gives me a number. Okay? The information theorist Fisher information, okay, is basically just a function of a density. Okay, in the usual senses you know it, right? So density on Rn. The information theorist Fisher information is just a function of that density, just a single number, like the entropy or something like that. You see what I'm saying? There's no notion of parameter here at all. So only in the special case, well, I shouldn't say only, but in the special case, okay, where our parametric family of densities is with respect to a location parameter, then the statistician's Fisher information is the same for all parameters. Okay? And it coincides with the information theorist's Fisher information associated to the density of that noise. Okay? The formulas say it all. Okay? But I want to be clear that there's these two different types of Fisher information. This type of Fisher information is useful if we're thinking about trying to bound performance in statistical estimation problems, like we did previously. Okay? So there's a particular parameter, we want to know how accurately we can estimate that parameter. That's where statistician's Fisher information comes in. Okay? And for information theorist Fisher information, okay, appearing here, coincides with statistician's Fisher information if we're dealing with location parameter, but we'll see this appears, okay, also in other places. That's what we'll see soon. And they both play a role, and in some cases, they both appear together in the same formula. Okay? Two different types of Fisher information. Good.
Out of curiosity, does the textbook use similar conventions to you in dealing with these ambiguities?
Do textbooks or the textbook?
The textbook.
Yeah, so I don't know if they use exactly the same notation. I have converged to this notation as my personal favorite because I think it's the best. Okay? Yeah, because it makes a good point of distinguishing between these different things. Okay? There's a lot of, or for the most part, people work exclusively with one type of Fisher information or the other. In which case, they maybe call them both I, or they call them both J, or whatever. It can be kind of confusing. But in this class, we're going to treat both. Okay? And Effie, my student back there, raise your hand, wave, okay? He is scribing some notes for you guys, okay? No warranty on the quality. But the idea is he is recording these lectures and he will follow my notational conventions and they'll be available for you. But also, you guys are scribing your own notes, okay? By sitting here in class, yes? Good. Where am I? Okay, so let's go here. So now we have these two types of Fisher information. We see how they're connected. Okay, they're not completely different. They're not the same, but they're not totally different. Okay, you see actually this formula looks quite similar to that formula up there, actually. Like very similar. Okay, no surprise. Very good. Anyways, so that's the basic idea. So let me make one note. Okay? Because you may ask, where are we going with all this? Okay? Remember, I started out this part by saying, you know, in general, if we wanted to follow that procedure of trying to establish statistical bounds by using information measures, if we did the naive thing, we would have ended up with something linear in N instead of logarithmic in N. Okay, that's a problem. And so I'm just like fast forwarding everything I said very quickly to remind you, okay? And so Fisher information provides us with an alternative method for establishing statistical lower bounds. And we'll see, not today, but we'll see that Fisher information and entropy will eventually come together beautifully, okay? But not yet. We have to have some patience. But let me note, okay? On this point of talking about independent observations or conditionally independent observations, this is the reason why statisticians like Fisher information, okay? Namely, information is additive on independent or conditionally independent observations. Okay, namely, let x1, x2, and xn be IID drawn from the density for a particular choice of theta. So they're conditionally independent random variables, conditioned on theta. Okay, again, these random variables maybe take values in some really wacky space, or if you like, you can think about them as living in Rn, no problem. Okay, and we look at the score. Okay, let me write v theta of xn. If we look at the score, now how is the score defined for these? Well, it's the gradient of the log of the density of x1 and xn. There you go. And what is this density? Okay, these things are conditionally IID. So this is equal to product I f xi theta. Okay? Okay, and this is a density with respect to the product measure, lambda to the n, on xn. Okay, so again, just take lambda to be the big measure, for example, okay, or counting measure. Either of these cases, both the Euclidean case and the discrete case are familiar to you. In which case, if I want a density of conditionally independent random variables, the density is just the product of the individual densities, right? Okay, so then this thing is just equal to, isn't that beautiful, the log and the product work together, and we get a sum, I go down to n, gradient log fxi, which is sum from I is 1 to n of xi. And in particular, okay, the Fisher information, which is the second element of the score, since the score is second mean, or sorry, zero mean, right? The second moment of this sum will just be the sum of the second moments. Okay? By independence and zero mean. Independence and zero mean, this is the sum of I equal 1 to n Okay, so let's define this as say I in. Okay, so you see what's happening is that if I have conditionally independent realizations, the Fisher information is linear. Okay, so each observation, okay, provides me with a new boost of Fisher information. Okay, and basically Fisher information goes linearly in number of observations, and this will be key to establishing bonds on sample complexity, namely how does my estimation error, or how quickly can it decay with number of samples, okay? This is the key property here. This is really why statisticians like Fisher information, is that they can study sample complexity. So if you get a bond involving Fisher information, then as soon as you observe n conditionally independent samples, then I just plug in n times Fisher information in that bond, and it tells me precisely how my error might decay, okay, in number of samples. Okay, very good, so we'll pick up there next time. Any questions? Yeah.
Are we assuming that theta functions throughout distribution?
So theta here, we don't have a distribution of theta at all. Okay, theta is just a parameter in RD at this point. We haven't placed any sort of distribution on theta.
Okay, so I'm just a bit confused about conditioning.
The conditioning where?
So like, how do we go conditioning to the configuration?
Yeah, so basically it's like, this is a density given theta, right? So I fix the one value of theta, and then I observe, n observations done independently according to this particular density.
Yeah, so it's not conditioning the sense of parameter.
No, I mean, we call it conditioning or conditionally independent. This would be a conditional density.